I'll start in a minute. Okay, it's time to start. Okay. Yeah, you can see the screen, right? Yeah. Okay. So last time, in the last class, I did a kind of an informal introduction to CTL model checking through example. And before that, there were two things that we discussed, observations about the form of counterexamples for CTL properties, CTL and LTL properties, and also the general shape of infinite paths. So I want to kind of re-emphasize the points that I made last time in case there was some confusion. So what I observed, the first observation was that every infinite witness counterexample to CTL star property has to be of, this should be a lasso shaped path. Okay. So there was one comment that came up, which was, a good observation, that this one is true only for counterexamples for CTL star formula, not necessarily true for the shapes of all parts of a Kripke model. So I want to re-emphasize that observation is indeed correct. Okay, for all CTL star formulas, this happens to be true, and you can actually prove them by looking at formulas with different operators, and you can for simple one level nesting of temporal operators, it is quite simple. But for deeper nesting, you will have to convince yourself. You have to have an inductive argument by proving this thing. That indeed you can get a lasso shaped thing. Another observation which I want to make is that the bound and the length of the counterexample, that is what I'm saying is this is exactly both in terms of the pre-tail as well as the length to which you have to go before it lassos, is very much a function of the structure of the property. Okay. And that is for any given transition system. It also depends on the property. Okay, so for different properties, the bound on the length of the counterexample can vary. Okay. Now, I also made the observation that this fact that indeed it is a lasso shaped is exploited in some model checking methods. Okay, specifically that where there's one model checking method called bounded model checking, which is based on it's a counterexample based model checking. Kind of shows that it's an algorithm which is based on proving non-existence of increasingly larger and larger counterexamples, and that's why it's called bounded model checking. You can keep doing that until you hit the bound for that particular property. But this is not. We will look at this bounded model checking method a little bit later on. But the one that we will be talking about immediately in today's class and the, oh, sorry, so there's somebody here. Sweeney. Yeah. So, but the one that immediately we'll talk about, which I mentioned, is explicit state model checking, which analyzes the transition graph and the symbolic version of it. They are not bounded model checking, but they are, you know, for the lack of a better word, traditional model checking. So it doesn't exploit this counter. They are not counterexample looking, model checking methods that are based on counterexample, but rather they directly show whether a particular path is what it takes to a certain a path or a state satisfies that property. Yeah. So that's why it's also important to understand the, so these things, just to quickly restate, every CTL property can be expressed in terms of these three operators. And we notice that, so it is enough to, devise an algorithm to process each of them. And the model checking algorithm exploits the fact that every formula is a nested formula rooted at to one of these operators. Okay, and what we saw last time was for EX and EU, and through this example, all satisfying paths for formulas that start with EX and EU, they can be determined by inspecting only finite paths. Okay, assuming that you've already labeled the states in which the subformula is true, then checking EX and EU, you only need to look at finite path. So as shown in this example, if you want to do EX of P, all you need to do is to first label all the states where P is true, and then for each state, you see if its predecessor is, you can label the predecessor with EX of P. Similarly, and that's true for, for EU also. Sorry, for EU, you do the same thing. You start with P. Why is this? I don't know how to get rid of this. It's a bit bothersome, isn't it? Do you see this this toolbar here? I don't know how to get rid of it. Sorry. Okay, so I don't know how to get rid of that, sorry. Maybe if I go to full view, then it's going away. Yeah, okay, so that's, yeah. So while processing in general E of P UQ, you will have to do it multi-step, okay? So you start with P, then you label that with EF, a U of P, and then you have to check if it is in general P until, Q until P. You start with all the states, in which P is satisfied. So by the semantics of EU, since Q until P is also satisfied there. So you label that, that state, and then you move to its predecessor, and each predecessor where Q is true, you can label that with E of Q until P, and so on. Okay, you have to keep continuing, iterating this process until you have labeled as many as you are able to. Okay, so that's multiple steps. So that's the observation that I'm making here, that you can do it by just looking at paths that end, finite paths that end with P, in order to check the satisfaction of EQ until P. Okay, and that's what is that's the idea that is used in formulating the algorithm. Okay, as I said, this is an explicit state model checking algorithm, in that it looks at the transition graph in a graphical form, and then labels that transition graph with the formulas. Okay, labels each state of that graph, in which the subformulas of the given formula are true. Okay, so here is the algorithm. This is exactly the way it is stated in the book, and I've reproduced it here. So this is for checking EU. Okay. So you start in line 1. Okay, so first you label every state in which F2 is true. Okay, and as I noticed that is done recursively. So this one is the algorithm for labeling all states that satisfy F1 until F2, assuming that you have already labeled the transition graph with states that satisfy F2. So you initialize T to the set of all states, okay, in which that have been labeled with F2. And as I observed in that example, you can add the label E with F1 until F2 to those states as well. Because if F2, any state in which F2 is true, so is F1 until F2, and that's what this line is doing. And then you iterate the labeling process with looking at all the predecessors. Okay, so you choose a state inside in T, remove that from T, and you look at all the predecessors of S. Okay, all states T that map to S.
Can you repeat what exactly we're trying to do here? We're trying to find all the states that satisfies E of F1, U, F2.
F1 until F2, assuming that you've already labeled
F1 and F2.
Label the states. Yeah, you've already processed F1 and F2. Now, F1 and F2 could be a nested formula, in which case you would have, I'm assuming that you've already done this, okay, for that. Or if it is an atomic formula with predicate, then, so you just go through the state and then label them, okay? So that's what we're trying to do, yes, okay? So you start with F2. You collect all the states in which have been labeled with F2. You can, to those states, you can also add the label F1 until F2, because if F2 is true in that state itself, then F1 until F2 is true, is also true in that state.
Yeah? I have a question regarding the notation. What is this F2 belongs to label of S?
That's another CTL formula,
Yeah, I mean F2 is the CTL formula,
correct?
and label of S. What is that?
Label of S, as I said, okay, you remember that how we do it? We do it by labeling all the states, okay? The states, I mean, we just compute all the states in the transition graph, for which each of these subformula is true, okay? For every subformula in the formula that you're trying to model check with,
Okay, okay.
you do that, and that's what we're trying to do. So by labeling, I mean a label means you have, so you're labeling each of those states in the transition graph with the formula, a subformula of phi, including phi, which is true in that state. Okay, that's what I mean. A label is a formula, is a subformula of this. Okay, so you start with P and Q labeling Q, then you apply AU. I mean, of course, you would have converted this into some form that contains only EX, EU, and EG. Okay, so I'm now describing the procedure for labeling a formula, labeling a state with, to check if EU of F1 until FE of F1 until F2 satisfies. Okay, so that I can add to that state. I mean, I can label that state with U F1 until F2. Okay, so that, and I do that, so I label every state either, in which that is satisfied with that subformula. The one in which is not satisfied, I will not, add that label. I mean, you can label the negation of that, but and then once you reach the root of this formula, you would have collected all the states in which the formula that you're concerned with is true. Okay, and then you can check if the initial state is included in that. Yeah, so that's what I'm doing. So so I kind of illustrated on this. So that's, I'm now giving the formal algorithm. Yeah. Does that clear up your doubt?
Yeah.
Yeah, this is one step in the recursive process for the formula, okay? You do it bottom up, okay? And if the subformula is rooted in EU, you will use this procedure, okay? So I'm already assuming that the every state in the transition graph have been labeled with F1 or F2. The states in which F1 is true will be labeled with F1. States in which F2 is true will be labeled with F2. So given that, now you are trying to see which of those states can I add the label EF1 until F2 to. Okay, that's what this algorithm is doing. Okay, so you start with labeling of F2, and then regardless of whether F1 is true there in that state or not, you can add. That's the base case. You can add F1 until F2, because if F2 is true in any state, F1 until F2, there already exists a path, okay, which is just a singleton path. That's why you're adding F1 until F2 to that. Now you have to see, then you pick a, then you have to see if there is something that leads to in which, remember that. So all the states in which F1 is continuously true, but eventually leads to F2 is also a state in which can be labeled with EF1 until F2. And that's what is happening here. So you pick a state which has already been labeled with this, EF1 until F2. I mean, yeah, so T, and then if it does not have F1, the label F1 until F2, then you check if F1 is true. F1 is true in that predecessor state. Okay, you pick a state from here, which is already labeled with that. Okay, and then you take the predecessor. If that is already not labeled with, because it could have been labeled by early on, then you don't need to label it again. So if it is not, then you check if F1 is true in that. Okay, if F1 is true in T, and in the next state, you have F1 until F2, then you know that it is true in this state T as well, because the semantics of until EU F1 F2 requires that F1 has to be continuously true until you reach something in which F2 is true. So that's why you can add then T also to this thing, because there exists a path from that in which F1 until F2 is true. Okay, so if you look at this example, starting from P, this is the step in which I look at the predecessor. Since P is true in S2 and E F1, in this case, true until P is true. So I also add S1 to it. And that's what I'm doing here. This step, and then I add the predecessor to T, because I want to then check, iteratively if T's predecessor can also be one of T's predecessors can be labeled with F1 until F2. Okay, and you keep repeating this until you have no more state to be labeled. Okay, with then you end. Okay, so then you have labeled all the states in which in the transition graph that in which F1 until F2 is true. Okay, so yeah, there is a bigger example that we can go through. I mean, I've already gone through this example. It's not exactly Q until this. It's true until P. So where Q is actually true, F1 is true, but F2 is P. But you can kind of see that how it can be extended to Q. So instead of here, I'm just looking at the predecessor. True is obviously true, in everything, and then I'm labeling that with EF of P. But if you had Q, then you start with P, and then you go to all its predecessors, and it's in a transitive, and it's transitive, and you apply that transitively until, and then you're labeling all those states in which that Q is true. That leads to something in which that is already labeled with F1 until F2, and that's what you're doing here. Okay. So you can see processing this, processing each CTL operator. Okay. So as you can see, each step itself has a loop. Okay. In each of that, you will be starting with something which has already been labeled and looking at its predecessor, which means you are chasing, for each state, you're chasing R. Okay, that's why processing each CTL operator in this nest, which is nested in the formula, each of that step at most requires S, the sum of the size of S and size of R, because you're chasing the predecessor from each state. Okay, and so that's why that can be processed in in linear time in the sum of these states, and you will have to repeat that this thing, the inner loop for all the you have to do this for all the operators, right? So it'll take for the entire formula, it takes the size of the formula. If you had only EU, therefore it'll take F times S plus R. Yeah. So is that clear? Any questions there? Okay.
Not yet done for EG, right?
Yeah, that's the one that I'm moving to. Okay. So I have not done EG, and you will see that also takes, okay, S times R. So yeah, so EG is a little bit more complicated. Okay. And that is because the parts that you need to inspect in order to check if it satisfies or not can be, infinite, okay? Because EG requires to ascertain if there exists a path originating from the state in which its subformula continuously true ad infinitum, okay? And that's why you have to kind of now look at actually the structure of the parts in the Kripke model. Now, we went through this a little bit last time, okay? So any infinite path in a Kripke model can be expressed in this fashion: pi naught followed by pi 1. Pi naught is a finite prefix of states in M, is a path containing some finite states, and pi 1 is an infinite suffix such that every state in pi 1 occurs infinitely often. So every path has to be of this kind, because you can run this pi naught long enough so that you will at some point you would have exhausted the occurrences of all the states that only occur finitely many times in a path. After that, after which point you will only have states that occur infinitely often. Okay, so you can always get to a point, and that's how I'm so that's why I'm saying that you can always express it in this fashion, so that every state in in this suffix of the path will occur infinitely often. Therefore, and the only way you can have some state in a finite state system occurring infinitely often, if it occurs in some kind of a loop, that is some strongly connected component. Okay, for those of you, strongly connected component of the transition graph of M is one. It's a subgraph. Okay, in which every subgraph of M, in which every state, it's a subgraph in which every node is reachable from every other node in that subgraph. And strongly connected components is a very well, and there are algorithms to identify and enumerate all strongly connected components in a graph, and so that can be done. So, given that, that is why this, how this structure comes into play. So any path can then be expressed in this fashion, where each of these pi 1I is a cycle formed inside, maximal strongly connected component in M. To see an example, see for example in this case, what are the infinite paths? See from S1, we can go. In this case, there are two disjoint strongly connected maximal strongly connected components. I mean, there's a reason you can do this with by identifying non-maximal ones, but it is more efficient if you identify maximal strongly connected components. A strongly connected component is maximal if it is not a subgraph, I mean, a part of a bigger strongly connected component. So in this case, you have two strongly connected components, okay? So here is one from S1 to S2 and back, okay? Because every state in that is reachable from every other state. And so is this self loop in S3. So if you had this self loop, another self loop in S2, if the self loop was, instead of being in S3, if there was a loop back into S2, then this whole thing would be inside a maximal strongly connected component. But for this example, so you have two strongly connected components. So there will be one path in which pi naught is S naught, and then there'll be only one inside the omega brackets, which is S1, S2. Or you can have another infinite path, which is of the shape S naught, S1, S2, followed by S3, okay, infinitely often. So as you can see, if there are, if the maximal strongly connected components has multiple loops, cycles, loops embedded in them, then you have, different arbitrary combinations of those things. As for example, if instead of the self loop, there was a back loop to S2 from S3, then there will both the cycles will be inside the same strongly connected components, and then you can have, you can loop in S1, S2 for some time, and then you can go to a loop for S2, S3, an arbitrary number of times and keep repeating. That's also a possible thing, and that's the thing that we already discussed this last time. Okay. Just for illustration, so this is a non-deterministic union, much like in regular languages. As a matter of fact, each of these individual pi naught and these pieces are, can be regular expressions involving the states. Okay, and that's how that you generate. So as I pointed out last time, you can have arbitrary combinations of these things, non-deterministic, but you cannot have any thing that will end up counting the lengths of paths and so on. So they are not included. Except for that, you have these things. So the point that I'm making is, so this structure, the individual pi11 patterns pi11 through pi1n are determined by the cycles inside the strongly connected components, and and that's what this thing is the same. So now, as you can see, you must have, see, if you want, this gives you an idea of what it means, what kind of paths can satisfy, say, AG of, say, P, okay? So in order for AG of P to be, EG, okay? We have reduced, we eliminated A, forget about, we're looking at EG. So to check EG of P, what you will have to first is, if P is true in every state, say in this strongly connected component here, which is the case, then you know that every pi 1 omega, that you generate from this strongly connected components, on that AG of P is true. And any state which has a path, in this case like S naught, that there's a path leading from that state and goes into one of the states in the strongly connected connected component, and such that every state from that on that path, the prefix path leading to the strongly to the point where it joins the strongly connected component, on that if P is true, then EG of P is, you found a path in which P is continuously true on the infinite path originating from S naught. So did you get that point? So for example, that's for that reason, for example, this EG of not of P is not true, okay? Because, I mean, there is a strongly connected, no, EG of not P is true in some states. So you, in order to determine that, the way you do is, so there is a strongly connected component in which not P is true in every state. That is this one. And now you have to then check, okay, so this state, S3 itself, is a state in which EG of not P is true, because the infinite parts in that strongly that are generated by the strongly connected component, EG of not P is true, but there is no path from any other state leading into that strongly connected component in which not P is continuously true. So the only state in which EG of not P is true in this transition graph is S3. And you see the way I identified that was by identifying this pi 1, okay? And since pi 1 has to be some part of the strongly connected component, you identify that. Look for all the strongly connected components. First check if, the P, the atomic, the embedded formula, EG of 5, if that is true there, and then you do that. So, in other words, because this, for EG, to check EG of F1, ascertaining satisfaction on a path requires inspecting infinite paths, okay, as I said, and therefore you will have to, and then you can use this, by enumerating all the SCC and then doing the check. Okay, so what I described, the observation informally right now, is what is defined in this lemma, which forms the basis for the algorithm for checking EG of F1. It says that a state S in a Kripke model S satisfies EG of F1 if and only if the following conditions hold. The idea is that you first take a sub graph. You restrict the M to M prime such that you keep only those states in which F1 is true. And then you restrict your transition relation R prime to those, that subset of states, okay? So in this case, for example, if you want to check EG of P, you only retain that part of your transition graph in which the states have labels of P, okay, which is this part, S1, S0, S1, and S2, and you can remove that part, and you restrict the transition relation to that too. And then from there, in that sub-transition graph, these two conditions will have to hold good. That starting from any S in that S prime, okay, so you're only keeping those states in which F1 is already true. So every state satisfies F1. So from that state, if there exists a path that leads from S to Q in some maximal strongly connected component C of inside that graph of M prime, sorry. So then you know that S to Q, then you know that there is a path. Okay? I mean, yeah, so this is doing slightly differently. I mean, it is just eliminating those states in which F1 is not true from the transition graph and only keeping the other subgraph. And then you can check if if there is every state from which there is a path from that state leading all the way to some strongly connected component. Now that you have ensured that every state in your transition graph is F1, every such a path, on every such path, F1 should be continuously should hold good, and therefore that state S will have a path from which there exists, there exists a path. Okay, so that's what you're doing. So you could do similarly in order to check if EG of not of P, for example, in this toy example is true. So you only, yeah, so it is saying you get rid of all that part of the graph in which P is, you keep only that part in which not P is true, and then see if there is yeah, so then you will only have this subgraph of S3, and that's why only S3 is the only state in which EG of not of P is true. Yeah, so see, you can see the one-way implication. So the reverse implication, so if there exists a strongly connected component in which F1 is true, and then there is a path, it's obvious that there is an S will be a state in which there exists a path, okay, in which P continuously true. Now, the proof of this lemma in the forward direction from, if there is there is a state in M in which EG of F1 is true, that then there will be a strongly connected component is by this construction that I just now described, okay? Because the way that we construct this this path, and if there is a path that satisfies this, then you can always divide it in this fashion. And then, since pi 1, is a path of this kind, therefore that should have been generated by some strongly connected components. So by that construction itself, you can show the forward direction, and that's why this way of doing checking, computing states in which EG of F1 is true is correct and sound. Any questions here? So what are the two steps then that the algorithm, an algorithm based on these ideas that I said and the lemma would have in checking EG of F1? First is you just take the restriction, okay, the subgraph in which F1 is true, okay. I mean, you retain only those states in which F1 is true, and then you identify all the strongly connected components in that. And then from what you can do is from each of the states in that strongly connected component, since you know that all the the cycles in that they satisfy P, then you go look at all the predecessors from each of those states. So for example, in this case, once you restrict the graph, you can start from S1 and S2. From each of those states, then you see if there is a path coming into S1 in which there's a predecessor in which from S2, from S1, yes, there is one, that is S0, and therefore S0, S1, so then you know that there is a infinite path that satisfies EG of P. Okay? From S2 also there is a predecessor, but it is already contained inside P1, inside the SCC anyway. So that is, yeah. So in other words, yes, S1 is also a state. Every state in that strongly connected component is obviously will be included in EG. Okay, so S0, S1, and S2 will all be labeled with EG of P in this case, and that's the idea. Okay, so that's what this algorithm is based on. So you start with S prime. See, one other thing, okay, sometimes when you take this restriction, when you restrict, get M prime from M, and when you restrict R prime to the, you restrict the domain of that, the R prime may not be total anymore, okay, left total anymore, which means you may end up having some R, okay, which goes to another. In this case, that does not happen, but you can have something which has terminating states, but that's okay. But actually, that doesn't matter as far as this algorithm is concerned. You can even get rid of those kinds of dangling, those kinds of terminating states. So, any case, so what you do here is after computing that S prime, so every state in that every state, S prime is F1, all the states in which, yes, that's what you're restricted to. So then first, after that, you get all the maximal strongly connected components, okay, in that. And you take the union of all the states that appear on each of those maximal strongly connected components. There can be multiple strongly connected components, and you take the union of all the states in each of those strongly connected components, and that you put it in T, because you have to check any state that has a path leading into any one of these any one of the states inside these strongly connected components will have EG of F1 being true, and that's what you start with. Yeah, you can already add EG of F1, the label EG of F1 to each of those states there, because they are, as I observed, so those states are already in a strongly connected component in which every state satisfies F1. Therefore, every path leading, from that, from those states that all obviously exist. Every path is, has F1 being satisfied, continually. Therefore, EG of F1 is obviously true for those states, and they can be added as label. Now, this while loop here now does this, adding those states from which there is a path leading to some path, paths that states from which there is a path leading to one of these strongly connected components, and that's what this while loop does. Okay, so you choose an S from that, and for each of those states, you remove that state, and now you have to check, every predecessor from that, state. If that, if there exists a predecessor for which F1 is true, then you can add EG of F1. If that's not already labeled, then you can add EG of F1 to that, and that you're adding that state to T. Why? Because you have to then check if the predecessor of T itself can be added. Okay, and that's why you're adding this T here. Eventually, see, you are subtracting that thing here, but so once you have done all the predecessors of a particular state, and then you will get out of this for loop if there are no more. I mean, every predecessor from that state, either you can't label it with EG of F1 or it is already labeled. Then you will go to the outer loop to get the next state, which is similar to what is in enumerate all, check if from every state, from every predecessor state, if there is a path that leads to EG, to one of these strongly connected components. And that's what you're doing here, okay? So as you can see, except for the extra step of enumerating all the strongly connected, maximal strongly connected components in the graph, the rest of the labeling procedure here is pretty much similar. I mean, almost identical to checking EU, okay? Because you are, so pi1 is identified by this strongly connected component, by identifying the strongly connected component. Pi naught is done by looking at the finite prefix, and that's what is happening. Yeah, there are algorithms for enumerating all non-trivial maximal SCC. There are linear time algorithms in the size, the sum of the size of the number of states and relation, the transition relation. And so the rest of the thing requires, as the rest of the things of, identifying all the predecessors, that can also be done in order S plus R. Therefore, the whole thing is order S plus R. And so, and then you keep doing this for all the operators. So it is still, the overall complexity is still linear in the size of the the entire the formula and at least in the number of states and the size of the edges, okay, in the graph. One thing to note here is that this doesn't mean that this is a super efficient algorithm. I mean, the real explosion, as we earlier, where when I talked about in the modeling class about the state explosion problem, I told you that for any given like system that has n components, the number of states, okay, there can be an exponential explosion in the number of components that are composed, especially in concurrent systems, or the number of states in the data size of the state variables can be exponential. Okay? So if you had a 32-bit vector, then you will have 2 to the 32 number of states that you will have to explore. Okay? So while CTL formula is quite efficient in the size of the transition system and the size of the formula, it is still, due to the state explosion problem, it can blow up in terms of the size of the state. Therefore, that is where the explosion comes. Okay. So any questions?
So what is the memory complexity of such
Yeah, that's what. These are times. So the memory comes in terms of the state here. Okay.
So it is taking exponential memory.
Correct. Yeah. So that's why two points there. Yes, the memory is so that's why it's p-space complete. I mean, so there's the memory, it can blow up. So in this explicit state enumeration, so that the fact that there can be a state explosion can be a complete non-starter, okay? So because it requires you to, if you have to construct the transition graphs, God forbid, a priori, completely, I mean, that's how this algorithm, I've described it here, but this is a very naive version of an algorithm. But in any case, if you have to, the way that I've done is I'm assuming here that you have the entire state transition graph and you are enumerating all, somewhat, all, after enumerating things, you are doing paths, exploring the paths through, looking at the transition relation. Therefore, for the problem, if the state and the relation size of the relation itself is exponential, then you will run out of memory even if you have to construct the entire graph before doing it. It is even a non-starter. That's why when model checkers that are implemented based on this explicit enumeration approach never construct the transition graph a priori. They all do what is called on-the-fly model checking, in which the transition graph is built as lazily on a need basis. Okay? So that if, because the idea of all these things is to get to errors as quickly as possible. So if there is a violation, then you may be able to produce a witness to the violation even before you enumerate the entire statement. That is one. Okay. Number two, maybe the reachable state is very small, although the size of the state and transition relation can be huge. Therefore, if you incrementally construct that on the fly, then you may still be able to produce useful results. Okay, that is the why even tools based on explicit enumeration are still quite useful in practice, and they use all other kinds of ways of not doing it incrementally. But where symbolic model checking wins is that instead of even if you use formulas to represent S and R, then you can get an exponential amount of compactness in the representation of the transition graph. Okay? So therefore, where explicit state approaches can run out of memory pretty fast, pretty quickly, the sometimes symbolic model checking wins. Okay?
But even if you are doing something like a non-def, I think there is a worst case scenario where to search your graph, you may just end up having to store a queue that is so large that it is basically your entire graph or something like that, right?
Yeah, but the explicit state approach, yeah, if in the worst case, if it's, if the bug is, even if you use on-the-fly model checking, if it is so deeply embedded, somewhere deep inside the thing, in which the, where it is reachable. So this is kind of pretty much, it does kind of a depth first kind of a thing. So then you cannot do it. Whereas you will see that in symbolic model checking, the way it works is pretty different. Okay,
Yes.
so you can get multiple states in one step. Okay, in the reachability thing, and therefore it'll it can work. But of course, there are always and also here you end up in symbolic model checking, you end up reducing this to a SAT instance, SAT solving. And the SAT solvers, with all the engineering that have gone into it, can work wonders, okay, sometimes. So anyway, there are two different things, but worst case complexity is nothing you can't avoid, okay? So it hits you in any case. Okay, so what I want to do now is, maybe I'll go through an example before I take any questions. So this example is from the book, okay? So I first, wanted to maybe do another example to illustration, but I thought that since I didn't have the time, so I'm using the book, the example in the book. This is not a, very trivial Twilight thing that I showed you earlier. But after I show this, I think, as an exercise, just a, practice exercise, if you could do, if you could review these two algorithms on the mutex example that I showed in class, as well as the Peterson's mutual exclusion, for which you are constructing the transition graph as part of the assignment. If you can do that, I'm sure that any doubts, I'm sure you have lots of questions and doubts that you're probably even, in the process of formulating. So I don't fault you if you don't understand this thing completely. But I think if you do follow the simulate the algorithm on certain examples, it will be much clearer to you. Okay, so let me. So here is a microwave oven as given in the thing. So yeah, so there are these 4 state variables, Boolean state variables. Start, which says if the microwave is started. Close is thing if it is the microwave door is closed or not. If it is heating, in the process of heating something, that's that. And there are certain ways that you cannot operate that are not correct to operate the microwave oven. But for example, you can't start before you close. Okay, so in which case it will get into an error state. So those are the 4 variables that are tracked by the transition system. So these labels are on the edges are just for they're not part of the state. Okay, so they're just for illustrative purposes. Okay. So if you close door, then of course from this initial state, from the state, then close becomes true. Then if you yeah, before you can close, you can't start. That's why this transition leads to an error state. The transition from 1 to 2 leads to an error state, okay? After that, it doesn't matter whether you close after that or keep opening. You're in error states, okay? No matter what, the error is continuing. The only way to get out of these error states is to do a reset, in which case error becomes false, and then you can start doing it. So only by doing a reset can you get to this is actually a famous thing, okay, example that it's one of these. There are these, just like mutex example, mutual exclusion example as a standard, a typical example for model checking. This microwave one is also a typical example. So in any case, so once you close and then you start, you go into a state in which it is closed. Then you go into warm up where it is being heated. In that state, you can stay for certain, non-deterministically arbitrary number of transitions. And after which, once you open the door, you're back into the original thing. You can eat what you have cooked. Okay, so that is the thing. This is the default initial state, but here, since in our algorithm, we don't care about the initial states. The algorithm is such that we are accumulating, states in which various subformulas are true. So what we want to prove is if every path from the start state, if you're in the start state, every path originating from such a state, you will eventually reach a state in which the microwave is heating up. Okay, that's what you want to prove. First of all, is this even true for this transition system?
No, right?
Yeah, say it loud. Why so?
So, I mean, there is this loop that involves the door never being
Correct.
closed.
Yeah. So you see this loop. So anything, once you
1,
get
2,
into an area,
5,
you
3.
keep on doing like this. Yeah.
Yeah.
This one here.
Okay.
Yeah, obviously, that's quite reasonable. I mean, if you make an error, you can, and if you don't know how to get out of it, that's your problem. Okay, so that's okay. So, but as long as you don't do that, so you don't, you at least get to start without error, then you will eventually get to heat. Okay. So yeah, that's kind of the fairness. I mean, you can only verify this with fairness constraint. Okay, so that's why this example. Yeah, so mutex is also good in that respect. So that will also illustrate how you can do CTL model checking in fairness. I don't know if I'll get to that today, but let me try to finish this example. So the first step, as you know, this is A. You have to get it into this normal form in which every CTL operator is one of those universal operators, is EG and EF. Of course, F is also gotten rid of because this is EF, although it is shown here, it is true until this. Okay, so but we will keep EF. Okay. So first, to start with, labeling all the states with the atomic predicates start and not heat. Okay, so that is easily identified. Okay, so the states in which S start is true are 2, 5, 6, and 7. S not of heat is 1, 2, 3, and 5, 6. Then you do this one. Yeah. So you work your way up, bottom up. So you have to compute the states in which the set of all states in which EG of not of heat is true, and the set of all states in which start and EG of not is true, and so on. So EG. So let's see EG. So we already got EG. Therefore, what is the first step? You have to just restrict yourself to the not heat portion of your transition graph. Okay, so which means it is this portion on the left side. So 4 and 7 are excluded. So in that, the first step after that is to identify a maximal strongly connected component. There are several strongly connected components that are not maximal. There is one here, there's one here, between 1 and 3, between 2 and 5, okay? There's also one bigger one that takes you all the way down here, which contains both those smaller CC. So 1, 2, 5, 3, those states form a maximal strongly connected component. After that, what do you do? So what do you think S of EG of not heat is? As per the algorithm, okay? You can probably guess yourself. So every state on that, okay, we are looking at if there exists, what are the states for which there exists a path. So the states in which not heat is true is obviously a state in which EG of not heat is true, correct? Because not heat is true right there, okay? So there is a singleton path, okay, from so then, so I mean, I'm sorry, that's not the case. Okay, so every path, because, yeah, so every path that leads from here is going to be, because it is inside the strongly connected component. I mean, that's not the, so the reason that it's true. So every state inside this, it's not heat, it's part of a strongly connected component. And therefore, so every path, that is, originating from that is actually will remain inside the strongly connected component, therefore it is true. Therefore, 1, 2, 3, and 5 are which are part of the strongly connected component itself are all the states in which EG of not of heat is true. And there is nothing else, there's no other path that is leading into this strongly connected component on which not heat is true universally, okay? Because the only state outside the strongly connected component is this one, okay, in which not heat is true, but that is kind of a dangling state, okay? So there are paths from these two states, 4 and 7, into it, but look at, those states, 4 and 7, are not ones in which not of heat is true, okay? That is because heat is true in those states. Therefore, these are the only paths. Convinced?
Yeah.
Oh, no, I guess you're not. Yes or no? You should say yes or no.
Yes, it is fine.
So what is the set of states when you start an EG of not? This should be easy.
State 2 and 5.
Okay, so that does not require any, any complicated processing. So the next thing you do is EF. So you apply the check EF. Okay. So what do you do with this? So what is the procedure? Remember the check EF? Start with T is initialized to T2 and 5. That's the starting point. And after that, you obviously T and 5 are states in which EF is true, because EF requires that there exists a path in which eventually this start and e.g. if not heat is true. So 2 and 5 is a state in which that is true. Therefore, 2, 5 is there. So that's how you accumulate. And then you see the predecessor state to 2 and 5. So there is 2 and 5. What are its if there is a predecessor state, yeah. So
Every state will lead to that, right?
Yeah.
Each and every state will lead to that, right?
That's right. So yeah, because there is one from here. Okay. Yeah. Everything is leading into that. Okay. And even from here, you always go into that. Okay. So therefore, and in that, and from there, because that is on a, yeah. So that's why you get all of them. Okay. And the way you do this is through that predecessor tracing loop part of the algorithm. Okay. You start from 2 and 5, and then you go trace the predecessor here, so you add that, and then you add this, and then so on until every state has been labeled at which you stop. Okay. So what you want to do eventually is not of this, and therefore the not of that will be, because this is includes all the states, it is NT. Okay. And that's why this is not true, okay, for the, as we observed, someone observed in the beginning. So unless you make a fairness assumption that as long as you restrict yourself to the fair paths, where a fair path is defined as one in which you have started, the door is closed, and it is not error is true, then only then will it be true. Okay, so that's, we'll do it. Yeah, I'm going to stop here because I don't want to rush through the fairness part. So, and I want to stop here and take any questions you might have.
Sir, I had a question about assignment.
Zubin is here as well?
Yes, please.
Oh, okay, shoot.
So, in the example where we have to draw the transition graph of that code, so is it enough if we take less amount of PC variables? Because if we assign PC variable to each line of the code, the transition graph will become very big.
How do you define as vary? Okay, this is something that so how many lines are there in that
5 lines.
code? Okay, how many?
5 lines.
How many?
5 lines.
5 lines. So PC takes 5 values. Why will that be very big?
X takes 8 values.
Yeah.
So there'll be 8 into
That's
5.
I thought, we had said that for the transition graph, you could use.
I think for the PC, you only need 3 values for the start and for each
update.
No, no,
Yeah,
no,
that's
no,
what I was saying.
no,
Is
no,
it
no.
enough
So
if we take
let me do it. I don't believe that this is such a thing. I mean, so if you restrict yourself, okay, first of all, I really wanted one of the purpose of this assignment, Zubin, I know that you can restrict yourself to 3, okay? If you want to abstract the loop completely and then you treat the body as atomic, okay? You can do that. Now, but if you have, okay, 8, even if you use numbers, yeah, okay, 8 times 5 will be 40 is what you're saying. So if you want to show the transition graph for that thing, so it is too much is what you're saying. Yeah.
if we take 3 PC variables and I
Yeah,
check
I think as long as you define, see, here's a compromise. Okay, see, my purpose was to ensure, see, the purpose of assignments is that you'll be honest and read what is covered in the class and make an attempt to understand. I wanted you to be able to understand the encoding for the sequential program encoding that I've discussed in class, which requires you to do one instruction at a time, okay? So at least define the transition relation, if not the transition graph. The transition graph is just, a graph.
You haven't asked for transition relation.
No, maybe, yeah. So here is what I will say through this thing, okay? So even with numbers, I know that there is, 40, but I'm not sure if all 40 are actually reachable, okay?
Yeah, exactly. All 40 are not reachable, but
Then what do you mean? Okay, so you already answered the question. Okay, I'm trying to see. I want to see. I don't want to see. Sometimes these things can get very petty. Okay, so since it is not reachable now, I'm discussing already. So I know that the mutex example, the transition system, would yeah. I mean, there is probably not. So here, since there's only a small percentage of the thing is, you started with saying, oh, I'll have to do 40 states, okay? Now we have gotten to a point where how many of those things are reachable? Probably not many.
I checked
Okay?
that around 25 are reachable, but that's a
Okay,
really big
so what? So you're worried about writing, 25 on a thing?
yeah,
Okay.
yeah.
So
It becomes
I
very messy.
want,
I checked, sir.
yeah. So you're saying that it is hard to write 25.
Not
Huh?
hard, it's messy.
Well,
And
okay.
if you use only
So
3 PC variable, it
try,
looks more compact. That's what I
that
was
is the thing. No, there is no way. Okay. The transition graph is an explicit state thing. It is not meant to be done, but in some instances it is useful. So therefore we had done that. Okay. If indeed it is, maybe you could do ... somewhere. Okay. If not, at least let me modify the thing by saying draw the transition relation with PC taking those 5 values, okay? Even if you don't do the transition graph, okay? Can that be a compromise? Yeah?
Okay, but that we can use x as an integer, right? There we don't need x to make x to be represented as 3-bit values.
Yeah, try it with the 3-bit value and see what you,
It will be even more
I think
complicated.
the transition relation even for that is fairly compact, okay? If you define certain bit vector, I'm giving you the solution, man, okay? So, I mean, this is, even with bit vectors, and as, if you have certain layered bit vector operations, you can do it, okay? I've constructed, larger transition relations, to educate myself, this whole procedure, by hand, until my hand started aching, okay? So that I was able to, understand the nitty-gritties, okay? So, but nonetheless, even the transition relation at the bit vector level with appropriately chosen Boolean variables, I don't think it's very big, okay? Now, beyond that, I don't want to dwell on this. Okay. Sorry, because this is not adding a lot of depth to the discussion. Okay. So
Okay,
use
okay.
your judgment.
So either a transition graph or transition relation is fine, right?
Yeah, I think transition relation is fine. I guess in this case, the transition graph, we are not using it, isn't it, Zubin?
Uh,
We're not using the transition graph there, sorry.
No, we are not using the further problems, further sub-problems in that question is not dependent on a transition graph being constructed. That is the question.
because
No.
Yeah, then that is now it is clear. So that is not the gating any other thing. So as long as you write the transition relation, I'll be happy. Okay, we'll be happy. Okay. Does that answer your question?
so transition relation including the PC variable or not PC variable?
Including PC. Okay. Yes.
Okay. But in the code, the transition relation I used does not involve PC. You have stated that you do not require PC variable to be used in the encoding.
I just now answered your question. So I do want the actual encoding with PC for each line of instruction, so that you will get some exercise on doing, going through the way that we encoded in class. Okay. I want the transition, symbolic transition relation, both at the bit vector level with PC. Okay. And, even with the numbers. Are you still confused?
No, I'm saying the transition relation that we are going to use in our code, SMT-lib2. There you have stated that you did not really need to represent the program counter. That's what I was saying. That's what I was asking. So I have actually solved the problem by not using the program counter in the transition relation. That's what
I want a version of a transition relation. How you encode it into SMT lib is a different thing. I want a symbolic representation at the integer level with PC for all the lines, a version of the transition relation with PC. Okay.
And how many variables PC should be? 5 variables.
Well, you figure that thing out. You know what the PC is. I'm not going to answer that.
No, sir, I know the answer. But what I'm asking is, if PC is 3, then the code, then the relation looks more compact. Otherwise, just some relations which are obvious. That's all.
The what? I want PC. You have you read the slides that I covered in the class where how I do? I want exactly like that.
Okay.
I want exactly like that.
Okay.
One with the PC represented as one for each line, and X variables you can use a version with numbers, another with bit vectors. Okay.
Okay.
Do other people feel that this is a big issue? If they're still hanging around, I don't know. I don't see this as a big issue, okay? But I mean, I can see this as a big issue for transition graph, okay? So if you want to add, have 40 bubbles, okay? And yeah, even if, so even if it means that it's a little bit laborious and cumbersome, do it. Okay, so now, okay, anyway, what I've made a, decision is instead of transition graph, it's okay if you don't give the transition graph, but I want the transition relation encoded, okay, in the way that I've done the problem in class to be applied to this to this problem.
Okay, sir.
Okay. Any other questions? There are no more questions. I'll stop sharing and I'll see you next week.